A mass spectrometer is a precision instrument, but its core analytical engine, the electromagnetic field, is completely blind to neutral matter. To see a molecule, we first have to give it a net charge. That transformation happens right at the start, making the ion source the gateway to the rest of the machine. The specific method used to force that charge onto the molecule dictates exactly what chemical information survives to reach the detector. Every ion source must overcome two major physical hurdles. First, getting the sample into a vacuum-compatible gas phase, and second, precisely controlling how much energy is transferred during the ionization event. Because no single technique can perfectly solve both hurdles for every type of molecule, analytical chemists have engineered highly specific physical environments to extract specific types of data. We classify these environments along a spectrum of energy transfer, ranging from hard to soft ionization. Hard techniques impart a massive amount of excess internal energy to the sample molecules, forcing them into a highly excited state. The molecule simply cannot hold that much excess energy, so it relaxes through the violent rupture of its chemical bonds. This shatters the original structure, producing a cascade of lower mass fragment ions. Soft techniques, however, transfer minimal energy. The molecule absorbs just enough to take on a charge, allowing it to ionize without subsequent bond cleavage. These softer environments are optimized strictly for preserving the intact molecular mass, which is critical when analyzing fragile or complex compounds. Deciding between hard and soft ionization is a direct choice between mapping a molecule's internal architecture and accurately weighing its complete, unbroken structure. Electron ionization, or EI, is the primary hard technique used for small, volatile organics. Inside an EI source, a heated filament sits adjacent to the ion chamber. As gaseous molecules enter, they cross its path. The filament generates a continuous beam of high-energy electrons, standardized at 70 electron volts, bombarding the incoming analyte stream. A near-miss collision between a beam electron and a sample molecule strips an electron away. This yields a positively charged odd electron species, known as a radical cation. That 70 electron volt impact leaves the radical cation with significant excess internal energy. It vibrates until it fractures into multiple distinct smaller pieces. This chart displays the EI mass spectrum of 1-decanol. On the far right, the molecular ion peak at 158 is absent, the parent molecule decomposed. Instead, data is dominated by left-side peaks, like the 43 base peak, representing structural fragments. Because chemical bonds break in predictable ways, this extensive fragmentation creates a highly specific fingerprint, allowing chemists to identify the compound against vast spectral databases. While EI is unmatched for structural verification, it destroys the intact molecular weight and requires samples that can be vaporized into stable gases. To preserve the parent molecule, engineers developed chemical ionization, or CI, a method designed to dial down the energy transfer. CI uses the same hardware as EI, but operates at a higher pressure by flooding the chamber with a reagent gas, typically methane. Because the methane is far more abundant, the 70 electron volt beam ionizes the background gas first, leaving the analyte untouched. The ionized methane then collides with the neutral analyte, transferring a proton via a mild reaction. We can observe the output of this softer CI technique by looking at the data for that same 1-decanol sample. This spectrum is entirely different. On the right side, we see massive peaks at 157 and 141. These are pseudomolecular ions. Because almost no internal energy was transferred during the collision, the molecule remains mostly intact, clearly revealing its overall molecular weight. Notice the distinct absence of the smaller structural fragment peaks that crowded the left side of the earlier EI spectrum. CI solves the fragmentation problem. However, because it relies on gas phase collisions, it remains restricted to analyzing compounds that can be maintained in the vapor state. This brings us to a significant analytical wall: massive biological macromolecules. If you try to heat a protein into a gas to ionize it, you will completely destroy it. Electrospray ionization, or ESI, bypassed the vacuum requirement. It extracts intact ions directly from a liquid solution at atmospheric pressure. This schematic details the ESI process. Liquid analyte is pumped through a stainless steel needle raised to a high electric potential. This intense field polarizes the liquid, drawing it outward into a distinct Taylor cone. The tip ejects a fine mist of highly charged droplets. As the solvent evaporates in the gas flow, the physical size of the droplet shrinks. This packs the trapped electrical charges closer and closer together. Eventually, the droplet hits the Rayleigh limit, the critical threshold where the outward electrostatic repulsion of the positive charges overcomes the inward surface tension. The liquid droplet shrinks down continuously until the trapped charges repel with enough explosive force to violently tear the droplet completely apart. This coulombic explosion repeats in a continuous cascade, eventually leaving behind bare, isolated analyte ions floating in the gas phase. This mechanism gives ESI a unique trait, routinely affixing multiple charges to a single large molecule. Most standard mass analyzers have a limited detection range, often topping out at a mass-to-charge ratio of 1,500. By attaching multiple charges, ESI lowers the effective m/z ratio of a massive protein, pulling it into the detectable range of standard hardware. ESI is the critical bridge allowing mass spectrometry to map the liquid-based world of biology. Selecting an ion source is never arbitrary. It requires balancing the physical state of the sample against the specific data you require. We can govern this choice using a simple decision matrix. The horizontal axis represents volatility, while the vertical axis represents our analytical goal, ranging from structural fingerprinting to pure intact mass. Electron ionization maps to volatile samples, where structural fingerprinting is the primary goal. Chemical ionization also serves volatile samples, but shifts the goal upward to preserving the intact molecular mass. Electrospray ionization is the premier tool for non-volatile, massive compounds, where intact mass preservation is mandatory. While soft techniques give accurate molecular weights, they introduce new challenges, like ion suppression in ESI or finding the right reagent gas in CI. The physics of the ion source dictates exactly how a molecule transitions into the realm of data, defining the scope of what a mass spectrometer can actually see.